Good morning. This title contains a few words that I need to explain. The first essential dimension is going to be the last one to be explained, but nevertheless, I need to introduce at least a little bit of background. So whenever you talk about essential dimension, it's relative to a certain subfield that you fix. So here we're fixing some field little k that we're going to assume that is algebraically closed and of positive characteristic P. So for whatever we are doing, we do need the characteristic to be positive. This might not be super essential, but it simplifies many arguments so for this context, we are going to assume that little k is algebraically closed. And I think also in the paper, I assume that. I'm not sure why, but so let's keep this. Anyhow, every field F is a field containing little k in this context. So its characteristic is also P. And we're studying cyclic algebras over F. And the interesting case, in my opinion, is when the degree of the cyclic algebra coincides with the characteristic of the field. It creates some problems. So you have an algebra, which is cyclic of degree P over F. In principle, you have the cyclicity conjecture. So whenever you have a prime degree algebra over a field, one expects it to be cyclic. But we're not going to assume anything. We're just going to assume that the algebra is cyclic to begin with. It is known for p equals 2 and 3. Apart from that, it's unknown yet. But still, it has a very nice structure. I'm going to switch to the right-hand side. Yeah. So such an algebra has the following presentation. It's generated over F by some x and y, such that x to the p minus x is some alpha. So x generates a cyclic extension of F. By cyclic, we mean that its Galois group is cyclic. So it has a generator, and the generator maps x to x plus 1. You repeat it p times, it just becomes the identity map. You have an element inducing this automorphism. So you have some y such that y inverse is x plus 1. But then this y becomes central when you raise it to the power of p. So y to the p is some beta. And we denote this presentation by the Hilbert symbol alpha beta. When the characteristic is different from p, you have a symmetric symbol or almost symmetric symbol. Here it's not symmetric because alpha stands for the cyclic extension and beta stands for the inseparable extension generated by y. So this algebra has two natural field extensions of F, as we said. You have the one generated by x and the one generated by y. You might have more field extensions in between, but these are the two interesting ones that describe the presentation. So this is the cyclic extension, and that's the inseparable extension. And we're interested not only in the structure of one algebra, but also its relation to other cyclic algebras that are defined over the same field. So you have a field. Potentially, you might have numerous different cyclic algebras defined over this field, which is, for instance, the case that you have over the rational numbers. Over the real numbers, you have only one unique cyclic algebra, which is the Hamilton-Quaternion algebra. But in principle, you might have numerous algebras, and want to understand the connection between them. So they might be totally disconnected. They might not share anything. They might be isomorphic, and they might share something in common, in which case it might be a common subfield. So we say that two algebras are linked if they share a common maximal subfield. this A is, let's say, cyclically linked to another algebra B if they share a cyclic extension of the center, and it's inseparably linked to see if A and C share an inseparable extension of the center. And so that's these are the two notions that we're studying in this context. And the moment you have these two notions, it's a natural question to ask whether there's any connection between those two. Does one imply the other? And perhaps there's no connection between the two. So we want to know whether this implies that, or this implies that. And I'm not the first person to ask this question. Draxel in the 70s asked this question for the special case of P equals 2. For that case, he concluded that inseparable linkage implies cyclic linkage. It took, I think, 30 more years for Situ and Lam to produce a neater argument for this implication for the case of P equals 2. And then he also gave an example of cyclic linked pairs of quaternion algebras which are not inseparably linked. So we know
Also for P equal to 2.
for P equals 2. And about 15 years later, I wrote a paper generalizing that for arbitrary P. So we know that this is true for arbitrary P, and this is false for arbitrary P. So that's mine. But still, you might wonder if there's anything that you can add here to have a positive implication in this direction. So that's the picture. These are the type of questions that we are studying. So I wrote this paper that shows that this implies that for arbitrary P in 2016 or so. But several years later, during COVID time, together with Mathieu Florence and Kelly McKee, we came up with another argument implying this thing, which holds also not just for pairs, but also for any n-tuples of algebras, and also for degrees greater than P, P squared, P cubed, and so on. But for this lecture, I just want to focus on the trick, because this trick also says something about the essential dimension. So I'm going to give you the new proof for the old argument, the old statement. So the statement is theorem is that inseparable linkage implies cyclic linkage, and it's a new proof. So you have two algebras, let's say A and B, and they share an inseparable subfield. So you can write in principle A as alpha gamma and B as beta gamma. So what I did back then in 2016 was to use the trick of multiplying gamma by any norm coming from beta, which is okay, it works, but then you modify this slot on the right, which is not so crucial if you just want to prove the theorem, but if you want to say something about the essential dimension, you want to keep gamma as is and not change it, if possible. So the trick that we came up with is that the moment you have this y generating the inseparable extension, if instead of y, you look at y plus 1, so this is, let's say, gamma, and you just get gamma plus 1. So the moment you have a gamma here, you can just choose to have a gamma plus 1 just as well, to just be gamma plus 1. And then apparently you can show that you can modify the slots on the left without modifying the slots on the right. So it works this way. One thing you can always do is to add to the left-hand slot gamma times any power, any pth power of an element. So you can put here alpha plus gamma times t to the p for any t you want. That's legit. Okay. Now you can do the same thing here. So you can add gamma plus 1 times t to the p. But then another thing you can do is to add any arbitrary element. An arbitrary element is an element of the form x to the p minus x. So just choose x to be negative t. And then what you get is minus t to the p plus t. Now, why did I do that? I did that because then when you look at the equality alpha plus gamma t to the p equals beta plus gamma plus 1 times t to the p minus t to the p plus t, this just becomes a linear equation. It becomes a linear equation. Gamma times t to the p dies. And then you have t to the p minus t to the p, so they also die. So you get t equals alpha minus beta. And when you put that thing back in here and here, you just get a specific element delta. So you have A is equal to delta comma gamma, and B is equal to delta comma gamma plus 1, which is pretty neat. So now you take delta to be equal to alpha plus gamma times alpha to the p minus beta to the p. And then your A is just delta comma gamma, and your B is just delta comma gamma plus 1.
It's like a common slot lemma for the distance.
Yeah, exactly. But the nice thing here is that as a linked pair of algebras, they descend to a field of transcendence degree 2 instead of 3. You see, because these two algebras are now defined over little k adjoining gamma and delta.
But that doesn't this mean that there is more thing?
No.
You can put y plus 1 into
Yeah, but the multiplication rule, if you want to change this to, you have to multiply delta by gamma plus 1 over gamma or something like that. You need to look at the Kato-Milcom algebra to understand how it works. So it might be, I don't remember if it's gamma plus 1 over gamma or the opposite, but one of those has to work. So it's not, it doesn't mean that they are equal. You don't have to be isomorphic. But it does mean that they descend to a field of transcendence degree 2. So now I need to explain what essential dimension means. Any questions so far? So that's pretty easy algebra, right? It's not. I'm only doing easy stuff. So what do we mean by essential dimension? Essential dimension is something that you can define for any category in principle. You need a covariant factor, blah, blah, blah. So here I'm going to define it ad hoc for the situation that I'm studying. So when you take cyclic algebras of degree p, over F that are cyclically linked, the essential dimension of the pair AB is the minimal transcendence degree of a field which is intermediate between little k and F, to which A and B descend as cyclically linked algebras. So that's the essential dimension in this context. We mean you have A and B are defined over F, which contains little k, but there might be some intermediate field, E, to which they descend. So you have some A naught and B naught that are defined over E. They are cyclically linked over E. And when you extend scalars to F, they just become the original A and B. So you go over all those fields for which this works, and you choose the E for which the transcendence degree of the lowercase is the minimal, and this degree is the essential dimension pair. Yeah.
So that's something which may be very essential here.
Okay.
It's not only that A and B descend to the small field, you also want the linkage. to
Right.
descend.
Yeah, I want them to descend as linked pairs. Yeah.
So it's like,
Yeah. So
can you
in
define
principle,
it?
you have to define the functor. The functor maps fields containing F to the sets of all pairs of
Can you
linked
define a
algebras.
category of these pairs?
Yeah, you have to define it.
Just
Yeah, you have to look at this category.
same idea.
You cannot. The thing with essential dimension is that you fix the category, you have to stay in that category. Okay, which makes more sense because otherwise it's like when you take, for instance, an algebra of exponent 2 and degree 8. It's true that you should probably say not degree 8, but rather index 8. It's true that you can write it always as a tensor product of 4 quaternion algebras, but then this tensor product, if you just descend it as is, it might not still have index 8, it might have index 16. So all these questions about, yeah, of course, if you just write it as AB tensor CD, tensor EF, and so on, and you just descend blindly to the field little k with A, B, C, and so on, this new algebra, which over F is bra equivalent to your original algebra, might not remain of index 8, it might have index 16. So all these questions become more delicate when you fix the category. So it's the same here. But it works for our case, right? Because in our case, those A and B, which are inseparably linked, you can write them down as still cyclically linked and inseparably linked algebras over that smaller field to which we descend. So the corollary that we have in this context is that if A and B are inseparably linked, then the essential dimension of this pair is at most 2. It is actually, it's actually 2, because if the essential dimension is less than 2, then any cyclic algebra is just split, and then it's not interesting. So the moment you have a pair where at least one of the algebras is a division algebra, this is exactly 2 and not just less or equal to 2. So that's already something interesting, because when you just take two algebras which are cyclically linked, you know that you can write the first as alpha beta and the second as alpha gamma. So it's actually only a choice of 2 options, right? You have either essential dimension 3 or 2. So when the inseparably linked is 2. And now the question is, what happens in the opposite direction? So if the essential dimension is 2, does it mean that the algebras are inseparably linked? So we didn't really present it this way, but in a work that I wrote with Uzi and Shira Gilat, we gave an answer to this direction for p equals 2. And the answer is yes for p equals 2. But I'm going here, this lecture focuses on arbitrary p. So I'm not going to give a full answer to this implication because I don't have. But I can give a very similar implication for the essential p dimension. So I need to explain what the essential p dimension is. I'll switch to the other side of the board. So what do we mean by essential p dimension? So in principle, when you have A and B over F, you can take some prime to P extension. And just extend scalars to A tensor L and B tensor L. So you get 2 new algebras that are still cyclically linked. And there are some reasons to hope that things don't really change that much when you allow prime to P extensions, but they do occasionally change. For instance, if you look at cyclic extensions of degree P squared, the essential dimension of those extensions is 2 in the usual sense, but when you allow such extensions, it reduces to 1. So the essential p dimension of A and B is the minimal essential dimension of AL BL, where we let AL range over all the extensions prime to P. So the new theorem that I'm going to prove is that if the essential p dimension of A and B is less or equal to 2, then AL and BL are inseparably linked for some extension L prime to P, degree prime to P. So it's not quite the statement I want, but it's the same. I want up to this freedom of extending scalars to any prime to P extension. Which means
What do you assume when A and B stop?
cyclic algebras of degree P, which are cyclically linked over F.
What does it mean that the essential dimension is P? An object in the category which has an essential dimension.
You mean what I mean by essential dimension 3 or 2?
For a specific pair.
Yeah, it's what's written over there. You ask yourself whether you have what kind of fields you have to which the pair descends as a pair of cyclically linked algebras, and you check the transcendence degree that you get. If you only get 3, then it's 3. Otherwise, you might get 2 or something. Yeah. You can also ask, can we show that the essential dimension is really 3 and not 2? Which is a question that I can answer, and the answer is yes, it is 3. But I can show that there are pairs that do not descend to 2. Okay. Actually using such arguments, essentially. Because the essential, I can show that there are pairs which are not inseparably linked, and they do not become inseparably linked for any prime to P extension, and then the essential P dimension is 3. And the essential P dimension is less or equal to the essential dimension, so the essential dimension is also 3. But I do need this theorem for that. Okay, so now things are going to get a little bit more complicated. So I'm going to give you an argument, with a hand-wavy argument for why this is true, via some statements using homology groups and the Neustadt-Satz for these special fields. So I'll give you the exact statement that I want to prove and what kind of tools I need for proving it. And I think the reason why I'm presenting it is just because I think it's beautiful. I don't know if it's useful for anything. I like the way this statement involves many different theorems that are not so often used and are quite neat. So the theorem that I'm going to prove and then conclude this one is that if the symbol alpha, beta, gamma in the third cohomology group of the field is trivial, then alpha, beta, and alpha, gamma are inseparably linked for some extension of degree prime 2. So that's the actual statement I'm going to prove. Now, for those who are a little bit familiar, I'm not going to define this monster, okay, for this talk. Just accept it as a black box. So whenever I say something about it, I'm going to explain what kind of statement I'm taking from the literature. In order to define it properly, one needs to delve into this theory of differential forms over fields of characteristic P, which is a bit strange, but one can do that. And as tools, I'm going to use two nice statements. One is by Gilles from, I think, the year 2000, saying that this symbol is trivial if and only if gamma is a norm in the cyclic algebra alpha beta. It's not at all a trivial statement. It was proven in characteristic different from P by Suslin 15 years earlier. You need heavy machinery from algebraic geometry to understand what's going on here. But I'm just going to take that as is. So for now, this string just becomes this.
And it generalizes the result of Wedderburn from maybe 100 years before.
Nice.
For the cyclic algebra.
For sig, right,
The
yeah.
condition,
It extends, like it's the next
Yeah,
step, right? It's the next step.
yeah, maybe.
The result that Tuzi is referring to is that this algebra is trivial if and only if beta is a norm from the field extension generated by the algebra.
Computational criterion for splitting the cyclic algebra.
So Gilles is producing a statement for H3, which had been known for H2. But there's no equivalent statement for H4. And actually, Wedderburn's statement holds true also for cyclic algebras of degrees which are not prime. But this one is not true when you switch to H sub P squared. So we have Merkurev showed it for characteristic different for P, and with Kelly and Mattia, we showed it for characteristic P, that if you take P squared here, then this is not true anymore, this statement of Gilles. So bad things happen when you move from H2 to H3. Even worse things happen when you switch from H3 to H4. Anyhow, we don't care about high cohomology groups, just 3. 3 is high enough for us. So we need this one. The other statement is a very, very beautiful statement that I don't know who was the first to prove. I know it appears in a paper by Pfister from 1995, but it might be much earlier than that. And the statement is the following. If F is P special, then any system of M equations, homogeneous equations, of degree prime to P in more than M variables has a non-trivial solution. So everybody's familiar with the Nuchtel and Zatz of algebraic closed fields, also with the Bezout's lemma and everything. But this thing hasn't been cited that much. So I haven't seen many citations of this statement, at least not from Pfister's paper. Again, it might appear elsewhere as well. I just don't know. I don't know any other reference for that. Well, it's pretty strong, and I need that. So I'm going to prove now this statement. Okay? Using those. And as part of the argument, instead of saying there exists such an L which is of degree prime to P over F, I'm just going to extend everything to the P special closure. I should mention, a field is called P special if it has no prime to P extensions. Okay. So you can take a field and extend gradually by picking each time a prime to P extension and then taking the sole closure of that, and you get a field which is P special. And for the argument, it's enough to look at this one. So I'm just going to assume that that F is P special.
Is that the same as saying that the absolute Galois group is the Q?
Yeah, exactly. Probably.
It's more standard.
Whichever language you prefer. It's just translating. If Tamar were here, I would probably say that, right? It depends on the person. Some people are afraid of this language. Anyhow, so we assume without loss of generality that F is P special. And then instead of proving that the two algebras become inseparably linked, I'm just going to prove that they are inseparably linked. Okay. So we begin with the fact that this guy is trivial, so gamma is a norm in this algebra. So this is our A, and we have also our B in the background, which is alpha gamma. And I want to show that A and B are inseparably linked. So how do I do that? Just to clarify, when we say a norm, we mean the reduced norm. The reduced norm is just the determinant. These algebras are almost P by P matrix algebras. They become P by P matrix algebras when you extend scalars to the algebraic closure. And when you look through this embedding and you pick an element, you look at which matrix it is mapped to, and you compute its determinant, you get an element in the base field F, and this is what we call the norm. So there exists some Z in A whose norm is gamma. Okay, that's fine. Now look for some V in the field extension generated by the arbitrary root of alpha. So we look at this field extension, which is a subfield of A. For which the following forms are annihilated. So I'm looking at F1 of ZV, F2 of ZV, and so on, up to Fp minus 1 of ZV. So what are these things? So F1 through Fp minus 1, and also Fp, which is the norm, are the characteristic coefficients. So again, I'm assuming that people are somewhat familiar with this, but even if not, I'll explain. Again, you have this algebra, you can embed it into a matrix algebra, there you can take the determinant. Now, similarly, you can take the characteristic polynomial, and when you go over all the different matrices that arise from that, you get characteristic coefficients which are homogeneous polynomial forms. The first one is the trace, the last one is the determinant, the norm, but you have all those in between as well, depending on P, of course. If you P is equal to 2, you have only those two. And the degree is exactly the substrate. So the trace is a linear form, the second one is a quadratic form, this one is of degree P minus 1, and the norm is a degree P form. But I'm just requiring that these are trivial. So I can use Pfister's theorem. And now, how many variables do we have? We have P variables, but only P minus 1 equations. So by Pfister, there is such a V. So by Pfister, V exists. Okay, so we can find such a V because we have only P minus 1 homogeneous equations of degrees prime to P, but we have P variables. the variables are the elements spanning this field extension of P, of F. So you have 1 x squared and so on up to x to the P minus 1. So what do we get by finding this V? So we have now an element which is Z times V. We have an element W which is Z times V, and the norm of this element is going to be negative W to the P. Might be W to the P. I should, yeah, so it's actually going to be W to the P in this context. Because all the other, so you just plug it in to the characteristic polynomial and everything vanishes because all these characteristic coefficients vanish. So you get only the norm. And this guy, the norm is multiplicative, so it's the norm of Z times the norm of V. So it's gamma times the norm of V. And this is an element that lives inside of A. Okay, so you can write A as something, comma, gamma times the norm of V. But your B is alpha, comma, gamma. So you can write it as alpha, comma, gamma times any norm you want that comes from this field. So they're inseparably linked. So that's the proof. So how do we get the previous theorem from that? The only thing that you need is to notice that the moment the essential dimension is 2, then when you look at H3, it vanishes. The essential dimension 2 means if you're taking transcendence degree 2 over a field which are algebraically closed, then the cohomological dimension is at most 2, and the third cohomology group is trivial. So you can just use this theorem to show that when the essential P dimension is less or equal to 2, it means that A and B are inseparably linked. So that's the theorem that I mentioned. Are not inseparably linked, become inseparably linked for some prime to P extension. Another neat thing to notice is that when F is of cohomological dimension at most 2 and P special, inseparable linkage is just the same as being cyclically linked. So you have a family of fields which are not completely irrelevant. People do study them. I think Philippe Gilles wrote an entire book studying fields of cohomological dimension 2. And many of them are also P special in his book, so they are not completely useless. And for those fields, these two notions somehow coincide. So what are we left to do in this setting? So that's what we know. We still don't have the theorem without these prime to P extensions. So things to do, the to-do list for future master and PhD students. So one again is, what can we conclude this thing? Something with that. I believe it's true. I just don't know at the moment how to show that. It is true for, so it's true for,
I mean, without extending the field.
yeah. So for P equals 2, it works. So if for P equals 2, we know it works. I don't know, for one place to start would be for p equals 3, perhaps. And if it's not true, it will be nice to produce a specific example, a concrete example that shows it's not true. Another thing that repeat the same for characteristic.
For p equals 3, it's a question of quadratic form.
Right? Yeah. For p equals 3, we only need the field to be quadratically closed for the statement, or we extend for quadratic extension. So right, yeah. It should be a good place to start. If you can prove it for p equals 3, you might have a chance. If you cannot do it for p equals 3, then there's no chance we're going to do it. But if a counterexample exists, it might just as well exist for p equals 3, then it's also interesting. And when I say repeat for characteristic different from p, I mean you can even ask the same question. So it's not exactly this one, but among the things that you can notice, I didn't write it explicitly, but one statement that you can prove using this terminology is that if alpha, beta, gamma is trivial in H3, then the essential p dimension of alpha, beta, and alpha, gamma is also equal to 2. It's actually a result of the fact that they become inseparably linked. And this question is something they can ask also for characteristic different from p, because you're not talking here about inseparable linkage. It's just, you have the symbols. You can look at the usual symbol in the Galois group, the Galois cohomology group, and here you can look at the pair alpha, beta, and alpha, gamma. And for characteristic different from p, if p is equal to 2, I know the answer here is yes. So there is a potential here. I just don't know what kind of technique to use, but for p equals 2, I just have the theory of quadratic forms, which I can apply. So if p is equal to 2, for instance, I can write this pair as, let's say, a, b, and a, comma, b plus 1, even without using inseparable linkage. It just works from the way you play with the quadratic forms, which are the norm forms. So I think there's a potential of doing something here characteristic not p, but it requires somewhat different methods. That's all for today.